Okay, so actually I didn't think I would make this video because I'm a little tired. I've been making videos from start of the day to the end of the day. But hey, let's just do it. So window to IIT. Now these are actual questions that were asked. So let's do it. Question number 1. Okay, the pH of bloodstream is maintained by proper balance of H2CO3 and NaHCO3 concentration. What volume of 5 molar NaHCO3 solution should be mixed with a 10 milliliter sample of blood, which is 2 molar in H2CO3, so like 20 millimoles of H2CO3. In order to maintain a pH of 7.4 Ka for okay, that's 7.8 into 10 power negative 7. Okay, so pH is that, which means like 10 power negative 7.4 times our fraction, let's call that x. That thing is your Ka value, which is 7.8 into 10 power negative 7. That means x is 7.8 into 10 power 0.4. Now 0.4 is not what we deal with. We'll say 7.8 into 10 into 10 power negative 0.6. So that we can deal with 7.8 upon 4 into 10, which is 78 upon 4, which is so 1 and then 38. No, that doesn't work. 32 would work, but not 38. Okay, so 1 for 32 you need 8, then point. So wait, why 32? Go for 36, right? So 19 point, and then yeah, 436 is like 76, and then for that 2 it would be 19.5. Yeah, there we go. So the fraction is 19.5, or if written more correctly, this is like 39 upon 2, I think, right? So 39 upon 2 is the fraction. What, like this is the fraction of concentration of conjugate base, which is what's the conjugate base? HCO3 minus upon concentration of H2CO3. All right, so what volume of 5 molar NaHCO3 solution should be mixed with 10 milliliter sample of blood, which is 2 molar in H2CO3, right? So it's already 20 millimoles of H2CO3 over here. Then this must be 390 millimoles, right? And that's that's NaHCO3 volume. So for 390 millimoles, that would be 390 upon 5 milliliters, which is what, like 390 upon 5, that is 78 milliliter. So 78 milliliter, is that the thing? I don't know. Well, looks like that, right? So there we go, 78 in milliliters. Might be correct, might be wrong, we don't care. Question number 2. An aqueous solution of a metal bromide 0.05 molar, okay, saturated with H2S, right? And it should be capital W, but whatever. What is the minimum pH at which MS will precipitate? Oh, okay. So then the data is given. KSP for MS is this thing. Concentration of saturated H2S is 0.1. K1 and K2 are given for H2S, right? So the thing is like concentration of S2 minus times concentration of what, like M2 plus. If it's at equilibrium, then this must be what, KSP, which is 6 into 10 power negative 21. And let's say that the metal bromide completely dissociates. Is it correct? Yeah, it's correct to assume it just completely dissociates. Then it will be giving 0.05 molar M2 plus. And let's say that its concentration doesn't change all that much, right? So what will your S2 minus be? Then your concentration of S2 minus, that will be 6 into 10 power negative 21 upon this guy, which is 0.05, which is like 1 upon 20, right? 1 upon 2 is 0.5, and then that upon 10. So that's gonna be 12 into 10 power negative 20, which is like very, very, very small, right? Very small in comparison to 0.05. Cool. So now you know what concentration of S2 minus is. We need to find the other concentration as well. Saturated solution of H2S. What is the minimum pH at which this will happen? Minimum pH. So what happens when it becomes more basic? Yeah, when it becomes more basic, then you get more S2 minus. Right. So concentration of S2 minus times concentration of H plus, which we'll say is 10 power negative pH, that upon concentration of what, like HS minus, that is K2. And the thing is, we just know that S2 minus is this concentration, and we don't know what that concentration is. Okay, whatever. And similarly, you will have concentration of HS minus 10 power negative pH upon concentration of what, H2, yeah, concentration of H2S equal to K1, right? Then multiply these together, that will be, and let's say that you just put a lot of this solution. Okay, so question number 2, right, is saturated with H2S, right? So it's like you just put a solid of H2S in it, and then it will just keep on precipitating 0.1 molar H2S solution. So yeah, the concentration will just remain constant for H2S. So that's cool. So then we know so like this will just be 0.1. We can just put that over here, right? It's 0.1, and then let's multiply these together, right? SS minus. Then this will be concentration of S2 minus, which we now know is 12 to 10 power negative 20, and then 10 power negative 2 pH, right? That upon what's this guy? Yeah, this gets cancelled, and then this is just 0.1. So 0.1. That thing is K1, K2, and K1, K2 is 1.3 into 10 power negative 20. Oh, that's nice. This cancels. Right, so that goes over there, which is 10 power 2 pH is, okay, 12 upon 0.1 is just 120, and then that upon like 1.3, I think, which is 1200 upon 13. This is approximately 1, right? Something less than that, bigger than that. Okay, so about 2. pH is about 2. Yeah, should we go more accurate than that? I don't think. Say it's 2, about 2. Yeah. Next. No, wait, 2 pH is about 2. pH should be about 1 in that case, right? Next question. Question number 3. For this reaction, the equilibrium constant at 25 degrees Celsius is 4, okay, into this thing. So this reaction, where is the reaction symbol? Okay, this is the reaction, fine. Calculate the silver ion concentration in a solution which was originally 10 molar KCN, which was 0.1 molar in KCN and 0.3 molar in AgNO3. Okay, so 0.1 molar Cn minus 0.03 molar Ag plus. So let's say that all of that Ag plus is just converted to, yeah, so like for 0.03 you will need 0.06 molar, like that many concentration, that much of concentration will be consumed for Cn, right? Let's say all of that just goes back to AgCN, or maybe not. Let's not say that. Whatever, let's do it. Just do it. So x, however much was there, okay, upon 0.1 minus x, no, minus 2x, because 2 times of that, and 0.03 minus x, that is the deal, and this is equal to, oh wait, Cn is twice, so it should be squared over there. Cool, now this looks correct. Wait, but that's the backward reaction. We don't want the backward reaction, but the forward reaction. So it's like this upon x. Okay, and that is equal to what? And we just want what, like the silver ion. Okay, we'll do it anyway. And this is 4 into 10 power negative 19. Okay. uh yeah, well, first of all, you see that this must be positive, then that means like x is less than 0.05. Hey, that means if I send this x over there, then this whole quantity will be less than um, 0.2 into 10 power negative 19, which is like 2 into 10 power negative 20. Okay, right. So this quantity is less than that. How does this help? I don't know. I mean, look at it. It looks comparable for some reason. Wait, it's not just less than 0.05, it's also less than 0.03. So wow, that's even less. Fine, but what about it? Oh, so this is also like less than 0.03. Cool. Like these will be comparable, who knows? Right, that's obvious. And this thing is that's not gonna lead us anywhere. We have to just guess some kind of approximation or maybe solve this. Oh, solving this is just a problematic thing. 4 into 10 power negative 19. Look, that's very small. Okay, so if x is comparable to these concentrations, then we will never get to that small a number. And that means your x, like either of these two things must be like really, really small. And that means x is either very close to 0.03 or very close to 0.05, which happens after 0.03. So this guy must be like very small. So then we can say x is approximately 0.03. So we'll try to figure out what this thing is. This thing will be 0.11 and 0.06. So 0.04 squared upon 0.03 times 0.03 minus x is what is this quantity? That quantity is our concentration of Ag, right? So yeah, exactly. That's what we're gonna find. Once you find it, you just solve the question. Right, of course. And this thing is just, what was it? 4 into 10 power negative 19. Okay, so 16 upon 3 into 0.01 squared, so just 10 power negative 2 into 0.03 minus x is, call this thing concentration of Ag, you know, because why not? Right, we can solve this. This is 4. That goes over there, so it's like it's 10 power negative 17 now. So concentration of Ag plus is 3/4 into 10 power negative 17. This thing is just 0.75, so it's gonna be 7.5 into 10 power negative 18, I think. There we go. This is our answer. Yeah, hopefully. Okay, so next question. Question number 4. Okay, the degree of dissociation of water at 25 degrees Celsius is 1.82 to the power negative 7 percentage. What? Seriously? No, I don't want any percentages. It's just 1.82 to 10 power negative 9. Okay, so like alpha is 1.8 into 10 power negative, or just say it's 18 into 10 power negative 10. Cool. And density is 1 gram. Of course. I mean, oh, we already know this. Why are you telling me this? The ionic constant for water. Yeah, it's at 25 degrees. It's like just, why are you? Oh, it's different maybe because it wasn't 10 power negative 10, was it? I think it was different. Whatever. So the degree of dissociation is this guy, and the density initially was just this. That means it's like 1 upon 18 into 1000. It's like 10 power 3 molar. That was the concentration of water. So this times alpha, that will be 10 power negative 13 molar. Okay, that is not good. Definitely not good. Okay, so yeah, it's just that this thing is, that's how it is. Yes, right. So this quantity is our concentration of H plus and OH minus. So the ionic constant is just square of this. So it's like 10 power negative 26. Well, that's not there. Oh, come on. It's negative 7. So it's like 1.8 power negative 10, of course. That's the degree of dissociation. And then the density is just that. So, oh, it should be 10 power negative 3 over there. Right. Millicentigrade AC. So AC is like, yeah, this should be 10 power negative 3. Hey, have I been doing this incorrectly all of the time? No. Well, that can't be. Uh, Whatever. So this just goes on top. It becomes 1000. So like 10 power 3 basically. Yeah, that's how it should be. Wow. Was I doing this wrong the whole time? Okay, so this will now just be 10 power negative 7. That means square of that's like 10 power negative 14. Well, that is correct. That's exactly how it should be. Okay, there we go. So A, fourth A. But this is not something worth asking because like people are gonna answer just like that. Why did they even ask this? But this wasn't any trick question in there. So 5. Which one is more acidic in aqueous solution? Oh, that's chemistry now. It's not physical chemistry. So more acidic. So like which can be more. In this case, there's no H. So which of them is like more Lewis acidic? AlCl3 it is acidic. BeCl2 is also acidic. Yeah, both of these are Lewis acids. FeCl3 I don't know. I have no idea about it. Nickel Cl2. No, these are like, are these acids? Oh yeah, these are actually. So AlCl3 it is an acid, but how acidic is this and how acidic is this? Like both of these are used as Lewis acids. Nickel Cl2 I don't know. Okay, this is a very theoretical question. I'm not gonna do it. It's just facts. I'm not good with facts. So question number 6. Alright. Calculate the pH of an aqueous solution of 1 molar ammonium formate, assuming complete dissociation. pK of the formic acid is 3.8 and pKb is 4.8 for ammonia. And okay, formic acid. Yeah, just that guy. Right, SCOH. And ammonia. And ammonium formate is the salt. Right. Complete dissociation. What? pH of an aqueous solution of this ammonium formate, assuming complete dissociation. Hell, that's very weird. But oh yeah, actually we do consider complete dissociation most of the time. It's just that it's kind of like, yeah. So the ammonium formate actually does dissociate into ammonium and formate ions, and then those would hydrolyze. So dissociation and hydrolysis are two different things. That makes sense. So an electrolyte that can completely dissociate and is also of weak acid, weak base. For that, we can use the formulas that we create. And this also works. Like, yeah. So we know how to do it. It's just half of pKw, which is 14, plus pKa. pKa is 3.8 and minus pKb, which is minus 4.8. So this will be minus 1. So it's like 13 upon 2, 7.5. Or maybe there's some error in this, who knows. Okay, so 7.5 is our pH. That's like basic mildly. So 10 power negative 6.5 is concentration of OH minus. Yeah, I mean it's big enough, I think. No, it's not. Like, shouldn't there be participation of water in there as well? Like, won't that also do something? Because yeah, it's giving us that. Is there water participation in there or not? I don't know, because it's giving a very not good kind of value, like 7.5. It's like close to 7, I should say. It's not even doing anything. Okay, we don't know. We don't have time for going to the formula derivation or all. So question number 7. What is pH of 0.5 molar aqueous NaCN solution? So pKb of, oh, nice. I thought you would give us the pH of HCN. But yeah, so pKb is 4.7. And what's the pH of 0.5 molar aqueous? This guy. So yeah, like just C alpha square is C times K. That will give us the pOH value. Like C alpha is our concentration of OH minus. So your pOH, or I should say 2 times your pOH, is what, like pk minus negative log base 10 of C, right? So you're like just half of that. What's your pOH? It's half of, so what's the pkb? It is 4.7 minus log C. C is 0.5, so that's gonna be plus log of 2, that's plus 0.3. That's why this matches up, which is half of 5, and it's like 2.5. So pOH is 2.5. That means, well, yeah, this is a big value. Everything will work out. Cool. So pH, and what's our alpha though in this case? Like your, just like 10 power negative 2.5 is your concentration of OH minus, that upon C. C is, where is C over here? It's question number 7, right? So it's 0.5, so like 2 times of that. That is your alpha. Is that small? I think it's like 0.02. You would just ignore it, right? I think. Okay, and pH is 14 minus that, which is 11.5. So there we go. 11.5 is the pH. That's what you want, isn't it? 7th. pH, yeah. Okay, next question. Okay, the following acids have been arranged in the order of decreasing acid strength. Identify the correct order. Order of decreasing acid strength. Identify the correct order. Have been arranged. What does that even mean? I think they mean have to be arranged. And then finding whatever. I think in the options they mean have whatever. So acidity, huh? ClOH. Okay, that's pretty acidic. This is also pretty acidic. Okay, all of these. So Cl is more electronegative. I think that's why this thing will be more acidic, and this will be slightly less than that, and this will be slightly less than that. So 1 bigger than 2 bigger than 3. Does that look good? Yeah, I think it does. So 8A. 1 bigger than 2 bigger than 3. But of course it's inorganic chemistry at that point, and then there's so many exceptions and whatnot. Whatever. In the reaction, the Lewis acid is, it's I2, of course. It, and I1, I minus is acting as a base because it inserts its lone pair into somebody, and this guy takes its lone pair. And yeah, so this acid is I2. Number 10. If pKb for fluoride ion is, okay, 10.83, the ionization constant of hypochloric acid in water at this temperature is, ionization constant of hydrofluoric acid. Hydrofluoric acid. What does that mean? Like hydrochloric acid just means HOCl. This would be HOF. It's like F O attached to it, and then H. Is that what it is? No, it's like this, HO then F. So over here F is more electronegative, so it's gonna be negative like that. Oh no, this must be like this in that case for it actually to work. Yeah, that must be happening. I know that this can happen, but this can also happen. Which of them is the case? Anyway, so what we were doing is just an acid basically. Ionization constant of this guy. I think basically the equilibrium constant. Yeah, but that's the same thing as Kp. What? How does this? Oh, okay, fluoride ion. So F minus plus like okay that going to HF. That's what you are saying, and then ionization constant for this guy. It splits in some other way, maybe. Uh, how basically? It's gonna split like F minus plus OH plus. That is very weird. What? Like, no. How can that be? Or maybe like this guy will get another H2O beside it and it will form peroxide and H plus. So maybe like this could then convert to O2, but that's a very long process. So what? Like this guy ionizes in water. How? I don't understand what we want. Okay, let's just move on. Question number 11. Question number 11 is the solubility of A2X3 is Y mole decimeter cube. Oh, sorry, negative cube. Yeah, so 5 molar basically. Its solubility product is, come on, seriously. So yeah, just 2s squared times 3s cube. That's gonna be 4 into 27, which is 8 and 28. 108 y power 5. That's D. What kind of question was this though? I don't know. Maybe Na plus and He plus, which is a stronger Lewis acid? That's inorganic chemistry. That's not even okay. A stronger Lewis acid, I think Ag plus, because Na plus actually is very inert. Like yeah, and it's also like more metallic. As you go to the left of the periodic table, it just becomes more metallic. And Ag, we have seen that it precipitates down by combining with like halides and stuff. So, sorry, halogens. And so yeah, it should be a stronger Lewis acid probably. So 12th B maybe. Sorry, no, 12th Ag plus and reason. Come on, it's not like the 12th board exam where I have to give reasons and stuff. I'm not gonna give you a reason. Question number 13. A sample of AgCl was treated with 5 milliliter of 1.5 molar Na2CO3 solution to give Ag2CO3. Okay. 1.5 molar Na2CO3 to give Ag2. Okay, so it precipitates that. The remaining solution containing 0.06, okay, 0026 grams. Wait, why grams? Okay, of Cl minus per liter. Oh God. So the density is given. Calculate the solubility product of AgCl. So from this you can figure out what the concentration of Cl minus was. Fine. Then what will you do? So Ag2CO3 was completely precipitated. We can figure out how much of Cl minus like was there. So there's a bit of AgCl, also a bit of Ag2CO3, right? You know, like with this much to give Ag2CO3. Huh. And what happened to the Cl minus though? Oh, so KSP is it's like that kind of question where one of them precipitates first and the other salt doesn't get a chance to precipitate. And that means Cl minus is still free, roaming in the solution, doing whatever it wants. Wait a second, just wait. Okay, so I will have to go, unfortunately. So yeah, I'll see you guys in the next video. Bye.